Good morning, I'm Mr. Precella. I wanted to do a little business calculus today for my Math 1325 class. We're looking at absolute extrema on a closed interval. Here's the problem. Find the absolute extrema of the function f of x equals negative x to the fourth plus 18x squared minus 81 on the closed interval from negative 4 to positive 4. Remember that absolute extrema can occur either at the endpoints of the interval or at the critical numbers. So we need to find the critical numbers, which means we need to find f prime. So differentiating, we get a negative 4x cubed plus 36x. That's a polynomial function. So this thing's always defined, so therefore the derivative is also a polynomial function. It's always defined. So all we really need to know is when does the derivative equal 0. So setting the derivative equal to 0, we can factor out a negative 4x from both terms. That'll leave me an x squared. 36x divided by a negative 4x gives me a minus 9. And that's a difference of two squares, which we can then factor as x plus 3 times x minus 3. So I think we're about to get three critical numbers here. Looks like they're all within the specified interval. If I'd gotten a critical number of 5, since 5 isn't between negative 4 and positive 4, I'd have to discard it. But here I have, when does negative 4x equal 0? When x is 0. When is x plus 3 equal to 0? When x is negative 3. When is x minus 3 equal to 0? When x is positive 3. And now I'm going to make myself a table. I don't have to draw a number line and determine increasing or decreasing for absolute extrema on a closed interval. I just have to figure out which x value gives the biggest y coordinate when plugged into the original function, which x value gives the smallest y coordinate. So I'm going to make a table, x, and I'll go ahead and write the function. F of x is, what is that? It's a negative x to the fourth plus 18x squared minus 81. So I'm going to plug in negative 4. I have to plug in the endpoints of the interval, negative 4 and positive 4. I'll list them in numerical order. And then I had a negative 3, 0, and positive 3. So I'm going to go through. I'll plug in negative 4, negative 3, 0, 3, and positive 4. So start off plugging in negative 4. We have a negative 4 to the fourth plus 18 times negative 4 squared minus 81. Punching that into my calculator, I will get, let's see, I'm getting a negative 49. Hey, that's nice when you plug in positive 4. Negative 4 to the fourth and negative 4 squared is the same thing as positive 4 to the fourth and positive 4 squared. So we're going to get the same thing down here. Plugging in positive 4, we'll get a negative 49 as well. Plugging in negative 3. Substituting in negative 3, we get a negative, let's see, is this green ink showing? Negative 3 to the fourth plus 18 times negative 3 squared minus 81. That's giving me a y value of 0. Oh. Okay. And same thing when you plug in a positive 3, because the way it's being raised to even exponents. If you doubt me, you go ahead and you plug in 3 yourself. When you plug 3 into the original function, you'll get a 0 here as well. And finally, plugging in 0 for x. Plugging in 0, we get a negative 0 to the fourth plus 18 times 0 squared minus 81, that reduces very nicely just to negative 81. Which one of these y values is the biggest number? Which y value is the smallest number? Well, the smallest number is obvious. The smallest y value that we got out of the 5 numbers is negative 81. So there's the absolute minimum value of the function. Well, let's see. The largest y value we got, believe it or not, is 0. Here it is. 0 is the biggest y value. So 0 is the absolute maximum. Looking back up here at the original problem, let me make a note here, absolute max. So we come up here. The function has a, where are we? Right here. Make sure that's all on the screen. Yes, okay. Has an absolute value. No, it has an absolute maximum at, they don't want the value, they just want the x value. So it has an absolute maximum at 2 different x values, negative 3 and positive 3. So in this little box here, we'll type negative 3, comma, positive 3. The function has an absolute minimum. The smallest y value is that negative 81, and it occurs when x is equal to 0. So we type a 0 in there. Okay, we found the critical numbers. And then this isn't like local extrema, absolute extrema on a closed interval. You just have to compare all the y values at the critical numbers and the y values at the endpoints of the interval. In this case, the absolute maximum and absolute minimum occurred at the critical numbers. They could have occurred at the endpoints of the intervals. So next, I have a second one I want to do. Oh, by the way, right now, this semester, fall 2015, this is number 4 in my class's homework. So if you're having trouble with number 4 and it's fall 2015 over homework 9, then this should help you, I hope. Next one. Okay, let's see. Find the absolute extrema of the function, and there's the function on the closed interval from 2 to 4. Once again, it's absolute extrema on a closed interval. It's absolute extrema on a closed interval, so the absolute extrema will occur either at critical numbers or at the endpoints of the interval 2 and 4. First thing we need to do is find our critical numbers. And in order to do that, we better find the derivative. So when I look at this, it's obvious it's a quotient. So we need to know the derivative of the numerator, which is 1. The derivative of the denominator, what is that? Negative 1, I agree. So here we go. We're using the quotient rule. Using the quotient rule, we get f prime of x is equal to, it's the derivative of the numerator, 1, times the denominator, the original denominator, 6 minus x, minus the derivative of the denominator, a negative 1, times the original numerator. The derivative of the numerator times the denominator minus the derivative of the denominator times the original numerator all over the denominator squared. That becomes a plus. So we have a 6 minus x plus a 6 plus x. The x's are subtracting out. This is working out nicely. 6 plus 6 gives me a 12 over 6 minus x quantity squared. So we ask ourselves, when is the derivative equal to 0? When is the derivative undefined? So first of all, when is f prime equal to 0? Set the derivative equal to 0, 12 over 6 minus x quantity squared. When is a fraction equal to 0? A fraction is equal to 0 when its numerator is equal to 0. So, and to show that, you can say, okay, I'm going to multiply both sides by that denominator, 6 minus x squared. If you want to get rid of the denominator and you multiply both sides by 6 minus x squared, you've canceled the denominator and you're left with what? All you have is 12. That derivative is equal to 0 when 12 is equal to, what have we got here? 0 times 6 minus x squared, still 0. So when does 12 equal 0? Never. 12 never equals 0. So when is f prime equal to 0? Never. So we didn't get a critical number from that. Next we ask ourselves, when is f prime undefined? When is f prime undefined? Well, a fraction is undefined when the denominator is 0. That's one thing you might want to remember. A fraction is equal to 0 when its numerator is 0. A fraction is undefined when its denominator is 0. Well, when is that denominator equal to 0? When is 6 minus x squared equal to 0? The only way that's going to happen is if 6 minus x is equal to 0, which means that x would have to be 6. 6 isn't in the domain of the function, though, is it? 6 isn't. Let's see, I moved my paper as I was writing. Look at this. Not only is 6, the function not defined at 6, 6 isn't even in the interval from 2 to 4. So we have no critical numbers. There are no critical numbers. Six is not in the interval from 2 to 4. We're only concerned about the absolute extrema on the closed interval from 2 to 4, so we're going to have to compare the value. When we plug in, let's see, where is it? When we plug in 2, what do we get for y? When we plug in 4, what do we get for y? Let's see. So I'm going to make myself a table of values just like I did a moment ago. Okay, I'm going to just push this up. So I'll make a table of values. My x and my f of x, the original function was 6 plus x over 6 minus x. So I have to plug in 2 and 4. Those are the only numbers I have to plug in, the endpoints of the interval. Whichever y value here turns out to be biggest, that'll be the absolute maximum. Whichever y value turns out smallest, that's the absolute minimum. So plugging in 2, we get 8 over 6 minus 2 is a 4. 8 divided by 4, we have a y value of 2 there, okay? Now plugging in 4, what are we going to get? We're going to get a 10 over 6 minus 4 is 2. 10 divided by 2 is 5. Well, the biggest y value is 5, so that's my absolute maximum. The smallest y value is 2, that's my absolute minimum. So let's see, they want to know the x values at which these occur. So the absolute maximum occurred at x equals 4. The absolute maximum occurred at x equals 4. And the absolute minimum occurred at x equals 2. The absolute maximum occurred when x was 4. The absolute minimum occurred when x was 2. Once again, we found the critical numbers. It just so happened in this case, there weren't any in the interval from 2 to 4, so all we could compare was the value of the function at 2 and the value of the function at 4. Okay, one more I want to do. Let me shuffle these papers around some. Where is it? Here it is. Oh, by the way, the problem I just did, the one I just did, this one was like number 5. If you're enrolled in my class fall 2015, then that was number 5 in your homework, or just like number 5 in your homework, I should say. And one more. Here it is. A word problem. If the price charged for a candy bar is P of X cents, then X thousand candy bars will be sold in a certain city where P of X is equal to 153 minus X over 10. Find an expression for the total revenue from the sale of X thousand candy bars. Okay, so part A. We know that revenue is equal to price times quantity. We saw that in Math 1324 if you took that course. Revenue is equal to price times quantity. We know that they tell us that the price is 153 minus X over 10. 153 minus X over 10 times quantity. Now this is where you have to be careful. The quantity is X thousand. And so if X is 5, they're selling 5,000 candy bars. So I'm going to denote the quantity with 1,000 times X. And then we can distribute the 1,000X over the first set of parentheses. That's going to give me a very nice revenue function. I don't know why I'm saying it's nice. These numbers are sort of large. We're going to get a revenue function. 153 times 1,000X, that's 153,000X minus, so we're distributing there and there. When we multiply X over 10 by 1,000, you'll cancel a 10, so that'll just give me a 100. X times X, that's giving me a minus 100X squared. So here's my revenue function right there up here in this box. I'll write 153,000X minus 100X squared. Next, they want to know the X value that leads to the maximum revenue. Well, let's find the derivative. We need to find our critical number, so differentiating, that'll just give me a 153,000 minus the derivative of 100X squared. 2 times 100 is a 200X to the first power. This is these are polynomial functions. They're always defined, so all we need to know is when does this equal 0? That's when 200X is equal to 153,000. Divide both sides by 200. Dividing both sides by 200, I'm getting an X value of 765. So, if maximum revenue exists, it has to occur when they produce and sell 765,000 candy bars. The X value is 765. So, let's see. Where did B start? This is where B started, right there. Finding that X value that leads to maximum revenue. Why don't we go ahead and show that? This is a single critical number. We don't have a closed interval. So what we can do is we can say, let's just show that 765 is the one and only local maximum. Remember, with the single critical number theorem, if there's one and only one critical number, and that critical number corresponds to a local maximum, that means that number has to be the absolute maximum as well. So I'm looking at the sign of R prime. To the left of 765, I can test any non-negative number I want to. I think I'll test 0. That's easy to plug in. So right here, I'm going to test 0. Testing 0. R prime becomes 153,000 minus 0, so that's positive, hence increasing. To the right of 765, I could test something like 800. If I tested 800, if I plug that into R prime, 800, test 800, not test 0, I'm testing 800. Plugging in 800 into R prime, I'd get 153,000 minus, that'd be 160,000, which would certainly be negative and decreasing. That means a local maximum and therefore an absolute maximum occurs when x is equal to 765. When x is 765, right there, 765. The final part, part C, that's the tricky part. Okay, find the maximum revenue. Well, to find the revenue, you have to plug that 765 into the revenue function, okay? This is part C. So, we take the revenue function, we plug in 765. We're plugging in right there. That's 153,000 times 765 minus 100, just ignore that whole thing there, minus 100 times 765 squared. So you're plugging that in, and that's going to give you 153,120 times 765 minus 100 times. That's going to give me, here's what I'm getting. I'm getting 585 225 00. In my face-to-face class, the students had problems because they wanted to plug that in up here for the maximum revenue, and they were getting the wrong. It was being counted wrong. Remember something. Our revenue function is in terms of cents. Go back to the original problem. The original statement. This price is terms of cents. So it was price times quantity, but that's in terms of cents, not dollars. They want the revenue in terms of dollars. Notice that little dollar sign. So we're going to have to take that big number, divide it by 100. We're going to convert it to dollars. That'll drop off those last two zeros. So the revenue is actually 585,225. Is that on the display there? Yes. There it is. This revenue, when you plugged in the 765, that was in terms of cents. You have to divide by 100 cents to get it in terms of dollars. So right up here, the maximum revenue is $585,225. Oh, maybe I should box those answers in. Here was the answer to part A. Here's the answer to part B, and then that one there, the answer to part C. And this is like y'all's number 6 during fall 2015. This was like number 6 in homework number 9 over optimization and absolute extrema. Well, I hope this helped you get the hang of some of these homework problems over absolute extrema and optimization. I will take a break and get ready for my next class. You have a good day. Bye-bye.